Okay, so here are the questions, and we can add some more to this later if we want as well. We'll start with number 3 with question 6. Winnipeg Stadium has 4 entrances and 9 exits. How many ways can 2 people enter together but leave by different exits? This is a decisions question, and depending on how you look at it, you could decide this is 4 decisions or 3 decisions. I'm going to do it as 4 decisions. Person 1 enters, then person 2 enters, person 1 exits, and then person 2 exits. So that'll describe what each of those decisions are. Now, how many choices does person 1 have to enter? There's 4 entrances. How many choices does person 2 have to enter? 1. So sometimes people put the entry 1 into one space and say it's only one decision, because once person 1 decides, person 2 doesn't have a choice. But we could do it as 2 spaces like that, and it'll just be 4 and then 1. Then for exiting, person 1 has 9 choices, and since person 2 has to exit in a different way, there'll be 8 choices there. And 4 times 9 times 8 will give us the answer. What is that, 288? Question 8a. How many 5-digit numbers can be formed from 1, 2, 3, 4, 5 if the odd digits occupy the odd places? Now, one of the things that from these questions that I find that sometimes they don't do a great job is saying whether repetition can be allowed or not. Sometimes they assume if you're taking it from these numbers, then you're only allowed to use a number once. But usually your final exam and my tests, it's going to be clear if you're allowed to repeat or not. Okay? So for this one, if the odd digits occupy the odd places, this is odd, this is odd, this is odd. And that's our restriction. Now we have 3 choices of odd numbers that can go here, then 2 are left, then 1 is left. And then these ones, there's no restriction, but there's only even numbers left. So there'll be 2 and 1. Multiply all those together, and you get 12 ways. Number 9. How many 4-letter words are possible using the letters of Thursday? 2, 3, 4. Thursday has 8 letters, so it'd be 8, 7, 6, 5. This is equal to 8p4. No restrictions whatsoever. But then in part B, it says it has to end in a Y. So now there's only one choice for our last letter. There are 7 letters left. So we get 765 times 1. 210 ways. And in C, do not start with an R, but end with a Y. So this has to be a Y. Still one choice here. This one is not an R. So now there's only 6 choices here. The R can go back in, so still 6 choices, then 5 for 180. Question 16, then 17, then 18, then 19, then 20. So in 16, using the numbers 1, 2, 3, 5, 6, 8, and 0, no repetition, how many 4-digit numbers are possible? There is a restriction here. We can't start with 0. So of the 7 numbers, there's only 6 choices here, and then 6, then 5, then 4. In part B, how many are divisible by 5? Now we have restrictions in 2 places. There's a restriction on here. This still is not 0. And here we have 0 or 5. Can you see that, those restrictions overlap? That 0 affects both of those spaces. So as soon as your restrictions overlap, we will not be able to solve this directly. And we're going to have to use cases. So let's use our last restriction, because it's either 0 or 5, and we can break up our cases that way. If we end with a 0, giving us only one choice there, then there's no restriction on the first one anymore. It can be any of the numbers that are left, and we had 7, we've used up 0, so there's 6 left, then 5 numbers left, then 4 numbers left. Case 1, 120 ways. Case 2, we end with a 5. And now we still have to consider that this one's not a 0. We had 6 numbers left, but since it can't be 0, there's only 5 choices here. The 0 gets put back in. We have 5 numbers left, then 4. With cases, add up your cases in the end, and there's 220 ways. And in part C, how many are even? Well, for even numbers, our possibilities for the last number are 0, 2, 6, and 8. Again, this is not 0. So again, we have an overlap. So how do we deal with that overlap? Case 1, let's end in 0. Then there's no restrictions on the first one, so this will still be 6 numbers left. You could break this up if you wanted to into 4 different cases. End with 0, end with 2, end with 6, end with 8. But if you end in 2, 6, or 8, those cases are identical. Because no matter which one of those you end with, you still cannot have 0 to start. So if I have 3 choices here, that will leave 6 numbers left, but I can't use 0, so I only have 5 choices here. And now there's 5 numbers left because we can put 0 back in. And we'll get 25 times 12, 300. And this will be 120. Add those up and we'll get 420 in total. Is someone driving a car in next door, or what is? Okay. 17. How many numbers less than 700 have no repetition of digits? This is a cases question because there are 3-digit numbers with 3 spaces. If it's less than 700, can you see that your possibilities for the first digit are 1, 2, 3, 4, 5, 6? So that would give you 6 choices. You've used up 1 number. How many numbers are left? 9, then 8. What does that equal to? 432. And then case 2, we haven't considered a 2-digit number. The only restriction is that this is not a 0, giving you 9 and 9, 81. And then case 3 is a single-digit number. Add those all up, and we get, what is that, 513, 523. Because the last digit, if it's a 0, we have to say, is 0 a one-digit number? I think so. Yes. So that's a good question. Could we do it in one case where that we include the 0? So then we put 10, well, we put instead of 6 choices at the beginning, right? You put 7 choices because you could include 0. And that'll count my 2-digit numbers. Then how many choices do I have for the second one? Do I have 9? So the complicated thing is, does that have repetition of digits? No. But if you wanted to use the 3 spaces, you'd have to have 2 zeros to start with, which is going to cause some problems, that you could allow a 0 to repeat. Okay? Or what about this number? Does it have repetition of digits? No. But if I start with 0 at the beginning, then I'm repeating my 0. And so we do have to count this one as separate cases, because the 0, if we included it at the beginning, causes problems with the other digits later on. But it's a good strategy to think, well, why couldn't I just start with the 0 and then maybe it doesn't, but then you wouldn't count 003 or 070. Question 18. Using the digits 222, 3, 3, 4, 5, how many 7-digit numbers can be formed? Can you see that this is a Mississippi question, just with numbers instead of letters? We've got identical objects in that there's 3 2s and 2 3s. Now, life is okay in part A. It's in part B that life gets difficult, because the numbers have to be greater than 3.4 million. So greater than makes us think of cases. The numbers that are identical, we've got cases and we've got identical objects. It's going to be complicated. So let's start putting some spaces down. We have 1, 2, 3, 4, 5, 6, 7 numbers that need to be placed. We need to be greater than 3.4 million. In order to guarantee that, case 1, we could start with a 4 or a 5. If we start with either a 4 or a 5, that's going to be in the 4 millions or 5 millions. That's guaranteed bigger than 3.4 million. Now, the problem we run into is that these last 6 spaces, we still have 3 2s left, 2 3s, and something else, either the 4 or the 5, whichever one we didn't choose to begin with. Normally, we would put numbers into those spaces, but now, since we have identical objects, we're going to say, well, normally I'd put 6 factorial because it would go 6, 5, 4, 3, 2, 1. But because of the identical objects, I have to divide by 3 factorial and 2 factorial. And we do all 6 of those spaces at once. Case 1. Case 2, what haven't we counted? We haven't counted any numbers that start with a 3. 1, 2, 3, 4, 5, 6, 7. Now, even though there's more than one 3, if I want a 3 to begin with, how many choices do I have? Only 1, because I'm making that a 3. Doesn't matter that I have 2 3s, it's still going to be a 3 when I put that number in there. Now, if I want it to be bigger than 4.5 million, after the 3, I can put a 4 or a 5. Now, sometimes you have to be careful with the 4 because you might not be bigger than it, but can you see that if I put a 4 there, no matter what I put as my last numbers, I will get a number bigger than 3.4 million. So we have 2 choices here. Now, what's left? We're still left with 3 2s, 1 3, and either the 4 or the 5. This would normally be 5 factorial, but now we have to divide by 3 factorial. And there's part B. add those two cases together, and we'll get our total amount. Now part C, now we want them greater than 3.4 million with those repetition of numbers and divisible by 5. So we've got cases, we've got identical objects, and we've got another restriction all to play into this one. So we can see that we've got these different strategies, but sometimes all of these strategies come together in one question. So case 1, I'm going to start it off the same. If I want to guarantee that it's going to be larger, the only way that I can do that, since it has to be divisible by 5, the only option for the last number is a 5. That has to be a 5. And so the only way to guarantee that it's going to be bigger than 3.4 million is to start with the 4. What am I left with in the middle here? Still have 3 2's left and 2 3's. That'll be 5 factorial over 3 factorial, 2 factorial. This works out to 10. Case 2, what haven't we started with? We haven't started with a 3. Again, it has to end with a 5. We're starting with a 3. This one then has to be a 4. And in these 4 that are left, we have 3 2's and a 3. So this will be 4 factorial over 3 factorial, which is 4 ways. And we get 14 possibilities. Which I find this question really fascinating because it takes a fair bit of time, and your final answer is 14. We have some counting questions that we can get to like 6,855,000, some crazy big number very quickly. And it takes no time. And this one, to count all the possibilities, took a fair bit of time, and there's only 14 in the end. So it almost seems like it might have been faster just to try to write them all out. And number 19, how many ways can 5 men and 3 women be arranged in a row if there's a man at each end of the row? So there's 8 spaces. This is a restriction question because this has to be a man, and this has to be a man. So if we deal with our restrictions first, how many choices do we have for this first spot? 5. How many choices do we have for this one? 4. Are there any restrictions in the middle? No. So now there are 6 people left. I mean, we could do 6, 5, 4, 3, 2, 1, or you could have just written 6 factorial in the middle there for all of those. And we multiply that all together, and we get 1440? No, 14,400. There we go. Forgot a 0. Okay, that is the end of questions from example or exercise 3. Now from exercise 4, 1, 6, 7, 8, 10a. Number 1, there's 11 chairs. Chairs in a row. 1, 2, 3, 4, 5, 6. And people have to be seated in consecutive ones. Can you see that one possibility is they could be in the first 5, and then it would just be 5, 4, 3, 2, 1. Or they could be here, 5, 4, 3, 2, 1. Or here, 5, 4, 3, 2, 1. All of those are going to be 5 factorial. How many can there be? Well, If I start here, I will 1, 2, 3, 4, 5, end here. If I start here, I would end here. If I started here, I would end here. 4, 5, 6, 7, and I'd end at the end. There would be 7 cases that are all identical. So if one case is 5 factorial, I take this 5 factorial and multiply it by 7 and get 840 ways. Yes? That would be the strategy I would want you to use in that one. To recognize that 5 in a row is 5 factorial. And if I had 11 in a row, there's 7 different cases that are all identical. So you don't have to write out case 1 using chairs 1 to 5. Case 2 using chairs 2 to 6. Case 3 using chairs. You could just explain. Okay, now, as far as writing this, I would lose marks because I have no explanation. So a little explanation here. What does this mean? 5 people in a row. 7 identical cases. So there's a little explanation of what I did. Yes? Yeah, this one is consecutive, and those other ones, when 5 people come to sit into 11 different chairs, they don't have to be consecutive. So this one has that additional restriction on it, which makes it smaller. Question number 6. The letters of barrier are arranged all at the time. This is like a Mississippi question. Normally, this would be 7 factorial, but we have 3 R's. So there's part A. Part B, we have an identical objects question with a restriction. It has to begin with the letter R. 1, 2, 3, 4, 5, 6, 7. We have to start with the letter R. There's only one choice. You put an R there. Even though there's 3 R's, there's just one choice. You're starting with an R. Then what you have left, you're just left with Barry. How many ways can you rearrange Barry? Well, that would be 6 factorial, but now there's 2 R's in there that are identical. So we have 6 factorial, 2 factorial. And in C, it says you start with exactly 1 R, so we don't have any words that are RR or RRR. So we still start with an R, one choice, but then the second one is not an R, giving us 4 choices. We are left with 2 R's and 3 other letters. We don't know what these 3 other letters are because we either used up a B, an A, an I, or an E in that second space. But if we were rearranging those, it would normally be 5 factorial because you have 5 letters left, but you're going to have to divide by 2 factorial because there's still 2 R's there. Do you like these questions that combine strategies? No. Number 7. 8 boys are arranged in a row. 2 unruly boys are not permitted to sit together, nor are they allowed to sit on either end of the row. This is a good example of the not strategy. It's going to be easier to count them together than it is to count them apart. So what I'm going to do, again, the not strategy says count all the ways, then subtract the bad ways, and you'll be left with the good ways. Now, when I'm counting all the ways, I'm going to count all the ways where they're not on the ends, but could be together in the middle or apart in the middle. And then I'm going to subtract the bad ways where they're not on the ends, but they are together in the middle. Can you see if I would do that, I'd be left with all the ways they'd still not be on the ends, and they would not be in the middle together. So, 2, 3, 4, 5, 6, 7, 8. All the ways they're not here and not here, meaning I would have 6 boys that could sit there, 5 boys that could sit there, and then in the middle, I don't care. They could be together or they could be apart. That would be 6 factorial. That counts all the ways that they're not on the ends, but they could be together in the middle or not together in the middle. The bad ways, they're not here, they're not here, but they are together in the middle. And if they are together in the middle, that's a grouping strategy. Here is, I need 2 names for the bad boys. Kyle and Riley. Perfect. There they are grouped together, and we still have another 4 boys. I'll just number them 1, 2, 3, 4. How do we do a grouping strategy? Maybe I'll put these underneath. Grouping strategy says number of groups Can we see we have 5 groups? 4 individual boys are each an individual group, and then there's the group of the 2 together, multiplied by the permutations of each group, but the only group that's bigger than 1 are the bad boys, and that's 2 factorial. If we look at this, we have at the top, they're not on the ends, but they could be together or not together in the middle. And in the second one, the bad one, they're not on the ends, but they are together in the middle. If you subtract those, can you see that what you're left with is they're not on the ends and they're not together in the middle? So if we figure out the numbers here, 6 factorial times by 30, 2160, 21600. This will be 30 times 240, 7200. If we subtract those, 14400, is that what the answer is? Yes. You'd be allowed a calculator. Question number 8. How many 4-digit numbers greater than 5,364 are possible? Case 1. In order to guarantee that it's greater, start with, so our numbers that we're allowed to use are 1, 2, 3, 5, 7, 8. And we want greater than 5364. Can you see that if you start with a 7 or an 8, you're guaranteed to be larger? And we had 6 numbers to begin with. You've used up 1 number. $120 ways, case 1. Case 2, what haven't we started with? Start with 5. Wow. 1 choice. Now, in order to be greater than 5364, what would guarantee that it would be greater? 7. Than a 7 or an 8. Two choices there. We've used up 2 numbers of the 6. There's 4 left, then 3. 24 ways. What haven't we counted? Case 3. Start with 5, 3. One choice, one choice. We need to be greater than 5364. That means our third one has to be a 7 or 8. Since there's no 6 in this, this is going to be our last case. Sometimes you'd have to do 4 cases with a 4-digit number, but now we're going to be guaranteed bigger. We've used up 3 numbers. There's 3 left. Add them all up. 120 plus 24 plus 6. 150 numbers in total. And finally, 10a. Solve for n plus 2 factorial. Oh boy. Over 8 factorial, n minus 2 factorial equals 57 over 16. Lovely. How do you get rid of factorials? Expand the top one because it's bigger. When you expand the top one, you get n plus 2, n plus 1, n minus 1, and finally you get to n minus 2, which I'll stop at because that could cancel out with the n minus 2 on the bottom. I'm going to move my 8 factorial to the other side by multiplying by 8 factorial. My plan here is to get all my numbers on one side, all my variables on the other. At this point, we are not going to use an algebraic way to solve this, because on the left, we're going to get an n to the 4. And we could multiply that out and get an n to the 4. We could multiply the right side out. If you multiply the right side out, it's going to be very large. And then you could use your factor theorem and remainder theorem and try and factor this with a number that's in the, 50,000s, which doesn't have too many factors to check. Or what we could do is we could notice that on the left, we have 4 consecutive numbers. On the right, I have 57 divided by 16 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And my goal is to try and rearrange the right-hand side as just 4 numbers multiplied in a row. First of all, if I have 4 numbers multiplied in a row, I can't have a 16 on the bottom. Can you see that that 16 would cancel out with the 8 and the 2? And now I have 7 times 6 times 5 times 4 times 3 times 1 times 57. Is there a way to break up 57? Yes. What times what is 57? It's not in your 18 times table. 3 and 19. Perfect. So what are we left with? We are left with 3 times 19 times 7 times 6 times 5 times 4 times 3. Whew. We need to have 4 numbers in a row that are consecutive. The 19 is a hint. 19 is prime. Chances are that one of them has to be 19. Can we put other numbers together to get close to 19? Can you get either 20 or 18 by multiplying numbers? How? 3 and 6? 3 and 6 would make 18. Good. 5 and 4 would make 20. What are we left with? 3 and 7 make 21. So now if I rewrite these, I have 21 times 20 times 19 times 18. Which is n? The third one. Everybody's shaking their head. They don't like this question anymore. N is 19. Ugh. So I got it right? I get bonus marks? Nice. Thanks. I have to come to work next week, but I can have the week after that off? Oh, nice.